This is a video based from a question on the second year D2L self-tests for the math section. This is talking about the combined gas law. The question reads, if a compressor that has a compression ratio of 8:1 draws in atmospheric air at sea level at a temperature of 77 degrees Fahrenheit, what would the discharge temperature gauge read if the discharge pressure was 118 PSIG? So the first thing that we need to do with this type of problem is figure out what numbers we use with the different variables we could have for this type of problem. So if we start at the beginning of the problem, it lists what we have initially. So it talks about a compression ratio being 8:1. What this means is initially we have a volume of somewhere 8 cubic feet, 8 cubic meters, whatever it is, a volume of 8 that we are going to reduce to a volume of 1 unit. If you looked at a double acting or a single acting reciprocating compressor, something similar like this with a cylinder and a piston inside that cylinder, when the piston's at bottom dead center, we have the volume of 8. And as it travels to the top dead center, it's going to squish and reduce that volume, and we'll be left with a volume of 1. So from that information, I will use 8 as my V1 and 1 as my V2. It then says the atmospheric pressure at sea level, we can draw information from that being 14.7 PSIA is what we would see at sea level. That's the measure of the atmospheric pressure, or what gravity is pulling on that column of air above you. And the temperature was 77 degrees Fahrenheit. The second part of the question asks, we're looking for the temperature. If our pressure is 118 PSIG. So in order for this problem to work in the formula, we first have to convert the numbers that we've been given to absolute. Volume in and out is already an absolute. We don't need to do anything there. Same thing with P1. Because I see A here, this is a measure of the atmospheric pressure. It will tell us the exact pressure relative to the atmosphere. That's perfect. T1 is the first variable here we need to convert to absolute. And we do that by adding 460 to convert it to Rankine. This is basically converting it to a scale where we can't have a number lower than 0. So 460 added to 77 is 537 degrees Rankine. Next, we need to take 118 and add 14.7 to convert this to absolute pressure. This tells us what the discharge is on that compressor. So also another note to point out, always put the units in here to clearly make it visible that you've included or not included the absolute values for this type of problem. We have all of the values we need. Now we can put it into the formula. This is the combined gas law formula. This should tell us, with these values here, what T2 is. I'm just going to put those numbers in place. So P1 is 14.7. V1 was 8. T1 is 537. P2, 132.7 times V2, which was 1, and the variable we're looking for is T2. The first step I would take to solve this problem is solve the easy part, solve what you know already. So this part of the equation, let's solve it. All I would do is take my calculator, type in 14.7 times 8, and then divide by 537. If we round it, it'll give us 0.219. Next thing, we can do that part easy as well. 132.7 times 1 is 132.7. The next step I would take in this to solve this problem, instead of doing hard algebra, the trick I would use, and it works for any type of formula that has one number on this side here, and where we have a variable on the bottom and the number on the top of a fraction. If the variable is on the bottom of the fraction, switch places here with those two. So it becomes T2 is equal to 132.7 divided by 0.219. That'll be the easy way of figuring this out instead of doing the long algebra and everything else. Works quite well. The answer, 605.95 degrees Rankine. Remember, we started in Rankine here, so the T2 will be outputted in Rankine. The question reads and asks for the gauge temperature. In order to calculate the gauge temperature, most gauges read in either Celsius or Fahrenheit. So we're going to convert this back to Fahrenheit by subtracting 460. And the answer will be 145.95 degrees Fahrenheit. This is our answer here. Now this is an ideal gas law. If you were to actually build a compressor that would put out these kind of numbers in this situation, it wouldn't put out quite the same because this is the ideal gas law. Thanks for watching.